This computer. Good. So today is September 29th, 9:43, and I'm sharing the screen of the schedule, estimated schedule for the fall 2025, right? We are writing here. The exam is going to be next week. Time flies, right? Time flies. Let's see. Yeah, okay, we're gonna have chapters 1 and 2 only. There won't be time to cover chapter 3. Finish covering chapter 3, right? So let's stick to chapter 1 and 2 and the lab 1 that we did. And to the motion, we're doing to the motion. That's the second, let's see. Yeah, that's the second meeting on to the motion, on the lecture of to the motion. The first meeting on to the motion was last Wednesday. Okay, and one more student coming. Here you go. That's what I want to show you. And let's pick up where we left, right? Where we left into the motion, but let's just do a quick summary. We have scalar quantities. The summary, right? Summary what we have done, quick summary that what have done so far. Scalar quantities, that length, time, and mass. Those are the basic quantities, 3 of the 7 basic quantities. And then we come up with 2 other quantities that are also scalar. The distance traveled and speed. When it comes to vectorial quantities, we have all that stuff here. Force and position, right? Force and position are primary definitions. We didn't cover force yet. It's gonna come later on, so it's better that we put here down here instead, right? Since we're covering position, since we're covering motion only, how do we change the force here to the bottom? Once we get there, I will elaborate on that. And we started with position. That is a primary definition. Force is also a primary definition. We have displacement, which is a secondary definition. It's a definition that needs the primary definition of position. And then we have average velocity, then it becomes tertiary, right? Tertiary definition, the quaternary, and so on. For instantaneous velocity, average acceleration, then instantaneous acceleration. We didn't cover those 2 yet. We started covering this one right here, the instantaneous velocity. Okay, so, well, by the same token that we have displacement delta x in 1 dimension, we also have its 2 and 3D counterpart, which is represented by the symbol delta r. Okay, the average velocity vector follows from the displacement vector, and it parallels the 1D case as well. If the average velocity in the 1-dimensional space is delta x over delta t, the average acceleration vector is delta r over delta t. Okay, so you know, the average velocity vector is parallels. The average velocity is parallel. Okay, the actual average velocity vector is parallel to the displacement vector, and how do you display that in mathematical terms, right? In mathematical terms, we display that like that. Parallel. Those two bars means parallel. And then we go for the instantaneous velocity vectors. Just like we have in the one-dimensional case, we have to apply the limit delta t going to 0. If here's a finite number, here's going to be a finite vector. Finite vector. And now let's talk about the average acceleration vector, right? We didn't talk about that. I was elaborating on the instantaneous velocity vector. I'm going to come back to that. I'm going to come back to the instantaneous velocity vector. The direction of the instantaneous velocity will coincide with the direction of displacement vector as e tends to 0, okay? And we have already seen, okay? It happens that the instantaneous velocity vector is always tangent to the path the object takes in the 2D space, in the two-dimensional space. Okay? And that's something new compared to 1D motion. And that is something new compared to 1D motion, right? Compared to 1D motion. Going back to, here we go. Going back here to my graphs, right? Here we go. X-axis, Y-axis, origin of the X and Y-axis. This is the X, Y, Z axis, right? The three-dimensional representation of three-dimensional space. But let's go back to the two-dimensional space. And here's a point in the three-dimensional space. We go X again, Y. I'm repeating, right? And here's the path of the projectile. No, here's the path of the object. So let's say the object moves along this line from this point all the way down to this other point, right? Here's the initial position of the object. And here is the initial vector position R0. Okay, at time t equal to 0. Here are the coordinates of this point, x0 and y0. And let's not forget, the same reasoning applies also to an object moving the 3D space. The 3D space, is more difficult to draw, okay? But try to, and we do have computer programs that can be used to illustrate that, right? Let's see, is this in the textbook? Let's see. So Melissa is asking, let me see, 149, 2 minutes ago, right? Well, what do you mean if this is in the textbook? This illustration that you see right in here, Melissa? Or the three-dimensional illustration? I'm not hearing from Melissa. But if you want that, let's take that's a good question. Okay, let us go there to the y plus, and just to parallel what I'm doing. I have been blocked. What is that? Must be my VPNs. Okay, here you go. Now, why I cannot access y plus? Okay, here you go. Think I know. I'm using a VPN, and for some reason, some sites don't like that we use VPN. They block us. So I have to turn off my VPN. Right, so here you go. Log in. Let's log in here. Just gonna take a look at the book. There is a few things that's not in the book, right? Like the treatment of the how physics is built up. But most of it, yes, it is in the book. Here you go. Let's go right here. Book, launch. Kinematics in 2 dimension. Okay, so here you go. Displacement, velocity, and acceleration, right? Here you go. Look, same illustration that I have, right? Initial position, final position, right? Same illustration that I have, a different way, and in instantaneous velocity, delta r over delta t, right? And here you go. Here's the path of the object, of the car. So yes, it is in the book, okay? And the vector velocity is always tangent to the path of the object in the 2-dimensional space. Okay? So I guess that answers your question, right? Chapter 3. Now, keep on going here. Okay, that's the initial position, right? And that's how we represent mathematically the initial position vector. X naught, x hat, plus y naught, y hat. And we do the same for the velocity, right? Velocity, the same thing. Here you go. Here's the final position vector, right? Initial position, final position. And then what I'm going to do, I'm going to illustrate the delta r, the displacement vector, right? The displacement vector is going to be r final minus r initial. Here is the r final vector. Here's the minus r initial vector. Tail to head is the resulting vector, right? I'm summing those two vectors that you see right in here. I'm summing the RF vector with the minus R naught vector, which is just another way of saying that I'm subtracting R naught from RF. Okay? And here you go. And the average velocity vector is parallel to the delta R vector, right? If we want to know the instantaneous velocity vector, all we have to do is to shrink the delta t interval. By shrinking the delta t interval, we will have to shrink the delta r vector as well. There you go, and that's what we're doing, The average velocity is still parallel. Average velocity is still parallel to the delta r. But as delta r becomes smaller and smaller, this delta r vector tends towards a point, towards a direction that is tangent to this curve, okay? Delta r goes to 0, yes, but the instantaneous velocity vector is not going to be 0. The direction of the instantaneous velocity is going to be tangent to the path of the object. V1, V2, here go, 3 different velocity vectors. There are 2 different ways of illustrating this velocity vector, okay? One way is this one that I like it most, okay? Here you go. Here's the instantaneous velocity vector at this point. At this point. Let me send it to the back. Just to let you know, here you go. The arrow starts at the point, at the tangent point, okay? That's one way of illustrate this velocity vector. Okay, the arrow, the velocity vector, it starts at the tangent point. And let's see here. What the hell is this thing here? I'm a little bit bothered with this other Let's see. Interesting. What about here? Auto here, right? Condense me perfect. I'm not gonna bother with that. So strange. Okay. So I'm not gonna. The other point is this one right in here. And I'm going to send all of them to the bottom, send to back. Okay. Another different way of illustrating the velocity vector that's tangent to the curve. How does it? It's like that. You extend the velocity vector half of the velocity vector. The midpoint of the velocity vector is tangent to the curve. That's another way of illustrating this velocity vector. The point that's tangent to the curve. Some books do the first way, other books do the other way. Okay, either way is fine. I prefer the first one. I prefer the first one. Okay. I prefer the first one. Let's see what we have here. Okay. Now, going back here, note that this velocity vector, and I'm going to write it down another way of illustrating the velocity vector tangent to the path. It doesn't matter what type of motion it is, the velocity vector will always be tangent to the path of the object. Like that. And then what I want to do now, I want to show you the components of this vector. Okay? Note that this vector here, v1, not just v1, but all the other ones as well, right? v1, v2, and v3 has x and y components. View grid lines. Let's see. I like the grid lines so I can see what's straight and what is not straight, right? Here you go. We don't need to do that. I'm complicating too much. Let me do it simpler, okay? I'm just gonna draw the x and y components of the vector. Here you go. Here's the x component of the vector. I'm gonna put it dashed. Like that. Like that. Yeah, like that is better. And the y component of the vector. Like that, okay? v1x, v1y. Here you go. v1, v2, v3, and so on. What is this? Okay, this one. Yeah, we do not need this slide. I'll put that at the bottom. So we need this definition of instantaneous velocity to define the instantaneous, the average acceleration, right? Okay, V1, just repeating what I did before. Here you go. Now here's my object moving along the path, okay? Playing the movie, right? Let's get another one. More clear than that, we cannot, it's impossible, right? Here you go. That's the nice thing about PowerPoint and computers. We can do our own movies, low resolution movies, right? Here you go. Okay, so here you go. Let's play the movie and let's turn off the grids. Okay, here you go. As time goes by, this object moves in the two-dimensional space. Okay, that's my R naught, and this position vector changes in time, right? That's why I put the R as a function of time. As time goes by, right? Look what happens to the velocity vector position, right? And I can even, here you go. I'm going to okay, so 1, 2, 3. One more, right? 4. So I'm going to erase 1, 2, 3. Oops. Looks like I erased the wrong one now. 3, 4. Okay. And now we put the rest, right? We put the rest, the remaining vectors position. Because it was here, now it's going to be here. Because the position of the particle along the path is changing, the vector position is also changing, right? Here you go. One more. Ah. One more. One more. All right. And the final one. Playing the movie, right? Let's play the movie again. Here you go. Look how the vector position changes as the particle moves, right? And here's the delta R. We already seen that. Let's not beat a dead horse, right? And here is the velocity vector tangent to this to this path. I'm not going to do everything because it's too much work, right? But what about the acceleration vector, right? Let's start with the average acceleration vector. Here you go, average acceleration. Average acceleration vector is nothing but V final minus V initial. Okay? Again, as delta T goes to 0, so goes delta V, right? In very small numbers, one divided by another one. Oh, wait a minute. I wanted this thing elsewhere. Here you go. I want it here. Yeah, that's the one-dimensional case, right? Here you go. Here you go, like that. As delta T goes to 0, so delta V goes to 0 as well. But this very small number divided by another small number is going to be equal to a finite vector. And you go, oh, what a shame. I want the vector on the top of the whole finite word. Here you go. Vector, 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 vector. Vector symbol. Sometimes the keystrokes doesn't work as well, right? Which is this case here. Finite. So let's illustrate this average acceleration vector. Let's illustrate the average acceleration vector now, right? What you have to know about the average acceleration vector? I'm going to give you the final, the rule of thumb. I'm going to give you the rule of thumb, okay? And then we will be able to sort of prove that, okay? The both, let's see. Okay. Okay, note that the average acceleration vector is parallel to delta V. Parallel to the delta V vector. Okay, the delta V vector. So what we have to do, let's see, we have to pick up two different points, right, in our graph. Here you go, one here and another here. Let's get this one here. This one, and then I have to label two. I have to label two. So let's say this one is T equal to 0, right? Here you go. T equal to 0. Oh. T equal to 0. And now I'm going to erase everything else. Here you go. T equal to 0. Next one is T equal to T1. Okay. Because I'm naming that T equal to T1, I'm going to name this one as V1. Okay. Next is T equal to T2. And because I am mention that T as being T2, I'm going to mention that V2 as well. Okay? And so on. Right? So here you go. T3, and so on. Okay, so my A1 vector, what's going to be my A1 vector? My A1 vector, average AVG, comma 1, right, is going to be, let's see, comma 1, okay. Is going to be Let's see how I label them. That's gonna be V0. V0. V1, V2, and V3. That should be V3, okay? My A1 vector and average A1 vector. Huh, interesting. Let me copy this one. Right here, right? Make sure we have V0 here, right? And let's get the V1 as well. And I'm going to superimpose to that other graph that I V0. And it's very close, but that's okay. We deal with that. Okay. Remember that the average acceleration vector is going to be a vector that's going to lie anywhere between those 2 points, right? Anywhere between those 2 points. So, and it's going to be V final minus V initial, okay? So because we're talking about minus V initial, what we have to do, we have to change the direction of the V initial. Okay, and here you go. That's my minus V initial vector. And gotta put a negative right in here. And I'm going to erase this t as a function of t because V0 is not a function of t, right? V0 is a constant. V1 also is not a function of t, right? It's just the genetic velocity vector that is a function of t. Okay? In a point anywhere in midway between those 2 points, we are going to have our average acceleration vector. We sum one with the other, okay? We sum one with the other. So gotta put the tail of one at the head of the other, right? And the resulting average acceleration vector is going to be this one right in here. This average acceleration vector lies anywhere between those 2 points in my graph. And I can now write down the average acceleration vector. And what happened here? Copy and paste it. Copy and paste it. That's going to be V0. Get our, oops. Delta V is upstairs. Delta T is downstairs. Okay? And I'm going to put in a different color so there is no doubt about, and we got to shrink it a little bit, right? Make it look, and I put that in red color as well. Did you get the idea? Okay? That's an average velocity vector. And this average you can take from anywhere, right? Can be the average between those 2 points, can be even the average between this point here and the last one. Okay, let's do that. Let's just for practice sake. Just for practice sake. Here you go. I'm going to get the first and the last point. Okay? the first and the last point. To make my life simpler, I'm just going to, here you go, copy this point right here. I'm going to put the last point right in here. Let's not forget that my last vector is going to look something like the following, right? It's going to be tangent, so it's going to be somewhat like that. And then I'll call that, instead of V1, I'll call that Vn. And I call that T sub n. T sub n, okay? V naught doesn't change because I'm taking the same point. I'm going to eliminate this other point here, right? And now my new average acceleration vector n is going to be Vn minus V naught. It's going to be somewhere in between those 2 points. Let's, it needs to be defined, okay? Let's say it would be an average somewhere around here. At this point here, I have my V naught vector that doesn't change, minus V naught vector that doesn't change, right? And here I have the Vn vector that doesn't change either. This one we do not need anymore. And what I want to do, let's see. Yeah, I'm going to, here you go. I'm going to move this one right in here. And I want to illustrate the initial velocity vector that is supposed to be right in here. All I have to do is to change its direction. Right, here you go. And I'll label it V naught, positive V naught. Okay? And if you take the average acceleration vector between those 2 points, it's going to look somewhat like the following: tail, bring to front, tail, of the final vector, bring to front as well, tail of the initial vector, head of the final vector. That is going to be my average. Oops, this guy got to move a little bit more to the right, so it's not encroaching on the other, right? And now I can start thinking in terms of, again, of the instantaneous acceleration vector at this point, right? I can start thinking about the instantaneous acceleration vector at that very point. We don't need that anymore. Okay. To find out the instantaneous acceleration vector at that very point, what do we have to do? We have to shrink the interval, right? Here you go. Shrinking the interval. And now instead of writing average here, I'm going to just to put a sub n, right? How am I going to, I have to change my notation here now. You know what, I'll leave this notation like that, right? Shrinking the interval. So we go through this trouble, right, to find out what's the direction of the instantaneous velocity vector would be in this case. And in this specific case, now the instantaneous velocity vector. Okay, here you go. Minus V naught. Take this one out. This one, Vn. Slightly, let's see, like that. Vn minus V naught. You can see that in this case, the average acceleration vector is going to be relatively small, right? Because all those velocity vectors, they're almost the same, Bring to the front. Didn't make any difference? Okay, yeah, I know why. Okay, now I'll be able, oh no. Huh, what a shame. Okay, now I'll be able to bring it to the front. Here you go. That's the acceleration vector, right? Very small. As we shrink, we find something interesting. At this very specific point, notice what's happening here at this very point here, right? I'm going to remove the V vectors. At this very point, we are having a change in the concavity of the path. Do you see that? Because we are having a change in the concavity of the path, what does it mean? It means that the acceleration vector is changing direction as well. Okay? So at this very point where there is a change in the concavity of the path, the acceleration vector is going to be very close to zero. Okay? I'm going to take it out. And if you keep on playing this way, if you keep on doing that, here I did the average acceleration vector, the instantaneous acceleration vector for this point, right? If you keep on doing for the other points, what do we find? We do the same here. Let's say for a point midway between these other two. What are we going to find? We are going to find out that the instantaneous acceleration vector is going to be pointing towards the center of the concavity, okay? Towards the center of the concavity. It can be in either this direction, or this direction, okay? What cannot be is in this direction because it's not towards the center of concavity. This one is away from the center of the concavity. Do you get the idea? Okay, acceleration vector is going to look just like that. Instantaneous acceleration vector. And I'm going to write that down. So at this point in the past, it's going to be like that. Let's do for more, As this, and that can be proven mathematically, by the way. At this point here in the past, it's going to be somewhat like that. Okay? But at this point in the past where there is a change in the concavity, let's move this one right in here. But at this point right in here in the past, where we are having a change in the concavity toward downwards, right? Concavity backwards, anywhere between those two different concavities, we're going to have a vector acceleration that's going to be equal to zero. I'm going to do, and I'm going to represent the zero acceleration vector with a small dot. A small dot that is going to, okay, here you go. Let's see if I can shrink it even more. Format, bring to front, format shape, size and position. That's what I want. I'm gonna make it smaller. Yeah, better, right? And now this dot that you see right in here represents what? Represents the acceleration vector equal to 0. Okay, and I'm gonna put right in the middle of this other dot right in here. Okay, a little bit down, a little bit to the left. Can you do that? A little bit to the right. Let's see if I can get it. Oh no! Where is my slide? Let's see. Must be the next one. Yeah, A equal to 0. Okay. Equal to 0. Do you get the idea? We can write that down. If the velocity vector, okay, if the velocity vector is tangent to the path, comma, if the instantaneous velocity vector is tangent to the path, the instantaneous acceleration vector points towards the center of the cavity of the path. Okay? Average acceleration, let's see. I gotta organize it better, right? I have to organize it better. So let's see what I see right in here. Average acceleration. I don't need to say it's finite. Now I have to go instantaneous acceleration. Okay, instantaneous acceleration. I write in here. I will take advantage of this instantaneous acceleration vector. That's the one-dimensional. That is the 2 and 3-dimensional. Instantaneous V finite vector. Here you go. Finite vector. Finite vector. And this phrase goes upstairs. Note that the average acceleration vector is parallel to the delta V vector. It's parallel to the delta V vector. If the instantaneous velocity vector is tangent to the path, the instantaneous acceleration vector points towards the center of the cavity of the path. Also, at the point along the path where the cavity is changing, also at a point, at the point along the path where the cavity is changing, okay, comma, the instantaneous acceleration vector will be equal to 0, okay? Will be equal to 0. That's what you have to know. Like I said, on the other case, we do not know exactly where the direction of this vector acceleration is, but we do know that it's going to be towards the center of the concavity. And towards the center of concavity, can be any direction like that, like that, like that. What cannot be would be a direction like that, away from the concavity, okay? To find out the exact direction, we must have a numerical result, okay? To exactly draw exactly the direction of the vector. Okay. And then all these quantities can be written in terms of their x and y components. All those vector components, all those vectorial definitions can be written down in terms of the vector components. All these vectorial definitions can be written in terms of their xy components. R naught is x naught x hat plus y naught y hat. RF is xf x hat plus yf, and so on, right? Delta R is something like that. Average velocity vector also is going to have an x component and a y component, just like that. For the instantaneous velocity vector, we write them down like that. For the average acceleration vector, we write their components just like that. And the instantaneous acceleration vector, we write its components just like that. Okay? And here, just a simple example, a simple qualitative example. Okay? Qualitative example. Qualitative example. Given the path of the particle and the directions and magnitudes of two instantaneous velocity vectors, find the generic direction of the average acceleration vectors between points 1 and 2, right? So here you go. That's what's given in the problem. I did something similar to that, right? The points that are tangent, one is here, the other one is here. All right. So let's write down the solution, all right? Solution. Go back to the definition of the average acceleration vector. Delta V over delta T, V final minus V initial. In this case, the V final is going to be V2. The initial is going to be V1. You're going to sum those two vectors. And then you got to do the graphical analysis of those two vectors. V2 is in this direction, minus V1 is in the other direction, right? And then you connect the tail of the first one to the head of the second one, you get the direction of the average acceleration vector between those 2 points, like that. Here's delta V, here's average vector. Okay. And if we superimpose in the path, right? If we superimpose these acceleration vectors in the path of the object, we see that this average acceleration vector coincides with the direction that points towards the center of the concavity. Okay, coincides why? Because why does it coincide? It coincides because the initial and final velocity vectors, they are both belong to the same, they are both taken along the same concavity, right? I didn't put this final velocity vector here in the other end of the concavity. Okay, I put it, the final velocity vector, along the path that has the same concavity direction, not the same concavity, but the same concavity direction. Okay, what time is that? Almost time for our break, right? We have 21 students right now. But before, okay, so summary. Let's just summarize, use those few minutes to summarize what we did. Before we go into the break, summary of the genetic treatment of 2D and 3D motion. 1, you must have the path drawing the 2D, 3D space. Okay, you need the instantaneous velocity vector will always be tangent to the path. So if there is a question in the exam about that, I don't have to tell you. This is something that you have to memorize, okay? The instantaneous velocity vector will always be tangent to the path. Okay? The average acceleration vector will. Let's see. The average acceleration vector will point towards, let me change that because it's not complete. This point here is not completely true, okay? Point towards, the average acceleration vector will be parallel to the delta V vector, okay? Okay, and then here you go. The instantaneous acceleration vector will always point towards the concavity, the center of the concavity of the path. The center of the concavity of the path. Point towards the concavity of the path if the 2 points are at the edge. Okay, that will be parallel to delta V vector. Okay. This one applies also the average velocity, average acceleration vector. Okay, so here you go. Let's put points toward the concavity of the path if the 2 points are, let's see, are at a section of the path of a single concavity. Better this way. If the 2 points encompass 2 or more different concavities, nothing can be said about the genetic direction of the average acceleration vector. Okay, but however, you still can do the genetic vectorial math that I did. Okay. The instantaneous acceleration velocity vector, instantaneous acceleration vector will always point towards the center of the concavity of the path. If the point taken, okay, if the point taken, however, if the point taken along the path is a point where the concavity of the will go up, I'm gonna put this way, will 1 always point toward the center concavity of the path. However, if the point chosen, right, along the path, the point where the concavity is changing, comma, then the acceleration, the instantaneous, the acceleration, let's put the acceleration vector will be 0, like that. Like that. Okay? Summary. 243. Let's also, what types of graph do you have? 1D, 2D, and 3D motion. Let's talk about that too. It's going to be very quickly. We don't have to. In 1D motion, you already saw different graphs for 1D motion, right? What type of graph do we have in 1D, 2D, and 3D motion, right? One-dimensional motion, X versus T, V versus T, A versus T. And on the top of that, we also have the motion diagram that you saw, okay? Motion diagram for constant velocity and constant acceleration. In the two-dimensional space, you're going to have more graphs because now you have more variables. You have the X versus T, right? Two-dimensional motion. You also going to have the Y versus T graph, the Vx versus T and the Vy versus T graph. And I want to put this one there at the top because that's how we will start, right? That's the path of the particle. Path of the particle. That's one graph. Two-dimensional motion. For the three-dimensional motion, you know. For the three-dimensional motion, you know, is a path in the 3D space, path along the XYZ axis, or the 3D space, represented by Z as a function of X and Y. Okay? Then we have X versus T, Y versus T, Z versus T. Vx versus T, Vy versus T, Vz versus blah, 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 right? Total of 4. We can also have a motion diagram in the two-dimensional space too, right? But that's going to be a little bit more difficult to visualize. Let's write it down here. Motion diagram of the particle along the X dash Y axis. Motion diagram along the XYZ. Not axis, but XY space. Okay? XYZ space. That's a neat. We didn't finish that. That's just the genetic treatment. We are going to see now that we finished. This is the genetic treatment of 2D motion. We will see some specific examples, specific important examples. So you can have a better grasp of how this type of motion is, okay? Specific important examples. For instance, the projectile motion, and later on, the circular the uniform circular motion, projectile motion, uniform circular motion, okay? For instance, let me just the projectile motion and the uniform circular motion and others, okay? And others. The limit is your imagination. The limit is your imagination, okay? But at least those two you're going to see in detail, so you have a better grasp. Finish. We have finished, yeah. Two D motion examples, for instance. Projectile motion. So it's 249, right? 249, no, it's 10:49, right? 10:49 a.m. Break. 10:49 a.m. Any questions? To 11:04 a.m. Yeah. So I see you in 15 minutes. Okay? See you soon. I'm back here. And let's now cover projectile motion, right? A very important type of motion. At the time where this problem was people were trying to solve this problem back in the 1500s. It had an important application in canyoneering, right? If you have a cannon and you want to strike your enemy, whether you're at sea or on ground, you needed to know what would be the right inclination of your cannon, right? What would be the right velocity, initial velocity of your cannonball to strike your enemy. So at the time of Galileo, they were trying to solve this problem. They knew more or less that the path of the projectile was very close to that of a parabola just by observing the water from a fountain describing its arc in the X and Y space, right? In the two-dimensional space. They had a partial idea how that would work. But then, there were other problems like, how do you compensate for air drag, right? So it is and it was and it's still a very important problem. It's one of the projectile. And let me tell you what is the very definition of projectile motion. Here you go. Projectile motion 3.3. Okay. And let's define what's the definition of projectile. Projectile motion. Definition. For the sake of this course, projectile is an object that moves under the influence that moves with uniform acceleration given by g 9.8 meters per second squared. Okay. That moves in the two-dimensional space. Two-dimensional space with a uniform acceleration given by 9.8 meters per second squared. Given with a uniform acceleration in the downward direction, given by 9.8 meters per second squared. That's the very definition of projectile. In this case, we neglect, okay, air drag. If you introduce air drag, then it's no longer, type of motion is no longer that of a projectile. Don't forget, projectile has all sorts of definitions out there, but for the sake of this chapter, for the sake of this section, that's what I mean by a projectile and projectile motion. Let's get our drawings here. Okay. Let's see. We did, let's see. We don't need that. Okay, different acceleration vectors, okay? Visualizing. Interesting. Okay, I gotta get another one. Here you go. 2D motion examples right here. That's the one I want. 2D motion graphs. X graph, x-axis, y-axis, right? Origin of the axis. And then, well, those are the graphs, right, that we are going to have under, that I covered before. Okay, so here you go. Just before the break, I covered that, right? X, Y, you know, Y-X path of the projectile, of the object, right? X versus T, Y versus T, VX versus T, VY versus T, AX, blah, blah, blah. Okay, now I want to talk about projectile motion. Let's see if this one here. Yeah, here you go. In order to talk about projectile motion, just like before, we must have the X and Y axis that's gonna show us what's gonna be the path that the projectile is going to take, right? So here you go, X-axis, Y-axis, origin, and then what do I put there in the origin? I put the projectile itself, the object that we are going to propel, okay? As this object is propelled in the XY plane, it will be subjected just to an acceleration that's going to be along the vertical downward direction. And mathematically, we represent that as a vector equal to the g vector equal to minus g scalar y hat, where the g scalar is 9.8 meters per second squared. What else do we need to describe the motion of the projectile? We need the acceleration, right? Let's write it down. Okay. To describe the motion of a projectile, we need the following. One, let's put A. The initial position of the projectile. In this case that I'm illustrating, in this case, you put the projectile at the origin. at the origin of the x, y axis. B. What else do we need? We need the acceleration. The projectile will be subjected to, okay, and the acceleration in this case, you already know. Let's get here you go. I need something like that. And the acceleration minus g y hat, right? Like that. Like that. And I illustrated the acceleration right in here. We don't need that anymore, right? It's illustrated. What else do we need? We need the initial velocity vector. Okay, so that must be given because we have the projectile. The initial velocity vector. And by initial velocity vector, I mean V naught vector, okay? Which is going to be V naught along the x direction. Let's not forget to put a hat. V naught along the y direction. And I'm going to do the same thing for the item number A, right? Item number A. Initial position of the projectile. In this case, we put the project. In this case, we put the projectile at the origin of the XY axis. And I'm going to put down here. Here you go. X naught, R naught is going to be equal to X naught, Y naught, right? Where X naught equal to Y naught equal to 0. That's the origin. Like that. Okay? So that's all we need. Okay, that's all we need. And here is the representation of the components of this vector, the vector velocity, initial velocity. Okay, and it's gonna look like something like that. We already know that if there is no air drag, the path that the projectile takes in the XY space, in the two-dimensional space, is going to be a parabola, but we can prove that mathematically, okay? And along this parabola, the acceleration vector will be the same because we have a uniform acceleration, okay? That we can write it down. I'm gonna copy and paste that in my notes as well. Like that. This illustration. There you go, like that. And because we have this path, you already know, right, that along this path, the velocity is going to change, right? Here you're gonna have a velocity vector. That's gonna look somewhat like that. Here you go. Here we are going to have another velocity vector that's gonna look somewhat like that. At the top of the parabola, we're going to want to be even more specific, okay? Here you go, it's gonna look like that. Looks like the thing is grid line. Looks like it's twisted a little bit, pointing towards downwards, right? Here you go. Velocity vector right in here. I didn't want to do that. Here you go. V naught back there, right? And so on, right? There is a vector velocity here, 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 all along this. Okay. Note the following. Note the following. Is uncoupled. Let's see. Oh, there's one more thing important. We need to realize that the motion along the x-axis is independent of the motion along the y-axis. So 1, 2, 3, 4 important points here. Okay? You apply all those 4 important points and you come up with the solution of the problem. Okay, so what we want to do here, obtain, example, right? Let's treat that as an example. Obtain the equations of motion of a projectile. Knowing all the above, okay? All the above. And then you write down the solution. Equations of motion are the equations that involve the acceleration, the velocity, and the position, right? In this case, you are going to have 6 equations of motion because they're going to have 2 components for each of these equations. 2 components for each of these equations. Okay, and I'm gonna write down, here you go. I need this one here. We start with the acceleration vector. Right, here you go. Acceleration vector is going to be the x component of the acceleration along the x hat direction. Plus the y component of the acceleration along the y direction. Since we have only a y component for the acceleration, it means that the acceleration along the x direction is going to be 0, right? I am emphasizing the fact that the acceleration along the x direction is 0. So we can rewrite that in terms of the components along. Here you go, ax equal to 0, ay equal to minus g. Like that. Our first set of our first equation of motion set. Acceleration next is going to be what? The velocity, right? Vx, Vy. Since the motion along the x and y axis are independent of each other, it means that the projectile will move with constant velocity along the x-axis, v naught x. Okay? Acceleration is equal to 0, which, by the way, is v naught cosine of theta. Since the motion is accelerated along the y-axis, it means that, it can be written down in terms of the initial velocity along the y-axis minus gt. And now we can finish for the other position, right? So here you go, x. Since it's uniform motion, all you gotta do is to use the equations for uniform motion. X naught plus vt, v naught equals sine of theta. But don't forget that the projectile is since the projectile is at the origin, we can eliminate the x naught from the equation. And now we do the same for the y. Y naught is uniformly accelerated, right? Y naught plus v. I'm going to do the following. I'm going to put v naught x here. Okay? Let's put v naught x here. V naught x. And then, we put v naught t. V naught t cosine of theta, right? V naught y times t minus half gt squared. Just like before, the projectile is at the origin of the axis, right? Here, v naught, sine of theta like that. So we are getting our equations of motion. Let's just copy it, paste it, right? There's nothing that we need to do here. All I have to do here is eliminate this term here to look at better. Here, I didn't finish, right? Let us finish this one here. V naught sine of theta. Okay. Now I can copy and paste here and eliminate this middle term. Here you go. Yep. Erase it. Oh, X. Okay. Right. Yeah, we have V naught Y, and now we change V naught Y to V naught sine of theta. Those are the equations of motion. Okay, those are the equations of motion for a projectile. There is another way of writing those equations of motion. Well, I already did, right? Yeah, let's see. Writing that down in terms of vectorial notation. Let's see if I can do that. Yeah, let's write that down in terms of vectorial notation. We have this vector notation here for the acceleration that already introduced you to, but I didn't show you the vectorial notation for the velocity. Go. V right? Vx x hat, Vy y hat, V naught cosine of theta x hat, right? V naught sine of theta minus gt. And then the position vector. The position vector. X hat, y hat. Right? And let me eliminate the middle term here to get a more compact notation, right? So that's what we get. Uniform velocity, uniform motion along the x-axis, accelerated motion along the y-axis. So we came up with the equations of motion, both in scalar form, both in terms of their components, and then in terms of written down in terms of vectors. What else can we do? Do you notice that we are using the same concept that we saw in the previous chapter, right? In chapter 2, uniformly accelerated and uniform motion, uniformly accelerated motion, right? Now let's look at another example, right? Example. Let's take a look here at the book. Here you go. We have this example here in the book. You can look at it. So, no, a projectile is propelled from the ground over a flat terrain with a non-initial velocity. Velocity and angle, right? No initial speed and angle. V naught and theta, respectively. Okay. find the range of the projectile, where range is defined as the distance it impacts the ground after being launched. Okay? Solution. If we go back here to the range is this distance here, from here to here. Okay? Find the range. We already have the equations of motion. And we also know that the moment the projectile impacts the ground, the position along the y-axis is going to be equal to 0, right? When the projectile is launched, its position along the y-axis is 0, but when it impacts the ground, its position is also going to be y equal to 0. Okay? So we have to use this piece of information to solve the problem. Okay? When the projectile impacts the ground, its y position will be y equal to 0. So let us use this information. Okay? And I'm going to use this. That's where I have to use, right? Because we don't have y anywhere else. 6 equations, right? The only one where y shows up is this one. So you have to use this set of equations. If we set y equal to 0 in the second equation, we can obtain how long the projectile remains airborne, right? That's what we can do. Once we determine how long the projectile remains airborne, we can substitute this result right in here to find out the range, okay? Once we obtain this amount of time, we can plug this value in the equation for x to obtain the range of the projectile. Okay, so here you go. Copy and paste, here you go. Right? Just make y equal to 0. And when y equal to 0, we solve for t. I'm gonna highlight t here, just to remind you that we're solving for t. It's a second order equation. Okay, but we do not need to solve, all we need to do here is to put t in evidence. Don't need to do any square root whatsoever, right? You're gonna see why. I'm going to put everything between parentheses. Right? Here you go. I'm gonna boldface this guy. This quadratic equation, of course, has two solutions, like every quadratic equation. One solution is t equal to 0. Quadratic equation has these two solutions. T1 equal to 0. And then we have T2, right? equal to 0. The other equation for T2 is going to be equal to 0 as well. T1 equal to 0 corresponds to the moment that the projectile was launched, right? So we don't want the solution. We don't want the first solution. We don't want the first solution for T because it corresponds to the moment the projectile was launched. The other solution corresponds to the instant when the projectile hits the ground. Or for this reason, okay, here, the first solution for this reason, it can be eliminated. Okay, now I'm going to eliminate the T1 here. We don't need T1, but we need the other one. Solving for T2. Solving for T2, right? Here you go, like that. Two upstairs, G downstairs. That's what T2 is all about. Two V naught sine of theta over G. 2V naught over G sine of theta. And now that we solve for how long the projectile stay airborne, we can state that X is going to be equal to the range of the projectile whenever T is equal to T2, right? And now we can continue our solution here. Substitute this guy right here for T2. Let us simplify our equation. Oh, no. I don't want to raise the initial, right? Let's see. Yeah. I don't want to raise, no, let's see. Okay, good, worked it. V naught combines with V naught. Sine of theta, cosine of theta times 2 is sine of 2 theta. And that's what's going to be the range of the projectile. The range of the projectile is going to be that. Notice that it goes with the square of the initial velocity. Twice as fast, notice that the range goes with the square of the initial speed. Twice as fast means 4 times the range, right? What times that? 1142. What else can we do before you go into the break? Let's see. Oh, yeah, let's, you know what? Let's use Excel in the equations of motion to plot the path of the projectile. Let's do that. We can do that. Let me get my Excel here. Excel is a very powerful software. I strongly encourage you folks to learn about this thing. Let's look at our roster here. Motion diagram, right? I did motion diagram for uniform motion. Now let's do a motion diagram for the projectile. Projectile motion. Projectile motion. And how we're going to do that, right? Here you go. We're going to need a t in seconds. We're not going to need the x position. That's going to be in meters. And I'm going to need the y position. That's going to be in meters as well. I'm going to need what? X naught, I'm going to put it equal to 0. Y naught, I'm going to put equal to 0. We are going to need the initial velocity. Okay, initial velocity. Or let's say initial speed. We're going to need the launch angle. Launch angle, symbol. This guy here is going to be upper script, superscript. Yeah, here you go. This one is going to be subscript, right? Make it look good, professional looking. Let's italicize the theta. Let's italicize V. Let's italicize the other parameters. Like that. Let's put an angle, let's say 20 degrees here. Okay, and I'm going to put, let's say 20 meters per second. 20 meters per second is what? 20 meters per second, 20 meters per second times 3,600 is going to be 72 kilometers per hour. Not bad. 72 kilometers per hour is approximately how many miles? Okay, kilometers per hour, right? Kilometers per hour, 20 times 3,600 divided by 1,000, right? And let's see how many miles per hour that is. 72 divided by 1.6. 45 miles an hour. That's what this initial speed is all about. Seems reasonable, right? It's not, I'm saying, ridiculously fast. Kilometers per hour. Miles per hour. I'm gonna move this theta angle right in here. And initial instant of time is 0. And then we write down the equations of motion along the x-axis. Is going to be V naught times cosine of 20 degrees, right? But what we need to do here, we have to convert this thing here to radians before we do this, the actual math. Okay, don't forget. Don't forget, Excel assumes that the term inside the cosine and the sine are already given in radians. And you can even test that, okay? Let's test that. Here you go. I'm going to put it cosine of 90 degrees, right? Everybody knows that cosine of 90 degrees is supposed to be 0, right? Let's see if we get 0. We don't get 0. We don't get 0 because Excel thinks that what the 90 that you put here is in radians, 90 radians, not 90 degrees. So first you have to convert this 90 degrees into radians, and we use this function of radian, the radians function. And now we get a very small number. We don't get exactly 0, but we get a very small number. See that 10 to minus 17 is, for all practical purposes, is 0. Okay, so I did the right thing. And let's see, at time t equal to 0, yeah, let's see. And then I have V naught cosine of theta times t, right? Times t. Here you go. I get 0. And I repeat that for y, the equation of motion that we saw before. V naught y, right? V naught sine of theta, V naught times sine, sine of theta. Don't forget to change to radians. V naught times sine of theta times t minus half the acceleration of gravity 9.85 times t squared. Remember, this is just for t equal to 0. But now I have to put other instants of time. Let's say every half a second. Let's do every tenth of a second. Every tenth of a second, right? And I gotta do something else too here. The theta angle must be, okay, $sign here because it's a constant. Oh, the V naught also. The D2 must be a $sign because it doesn't change, right? $sign for D2, $sign for G2. Okay, and now we can start calculating the positions, XY position, right, of the projectile. 1.87 meters away from the origin. I wonder, okay, and then we can do for the rest, right? Here you go. It's climbing. See that? The height of the projectile is climbing, is increasing, 2.1, 2.3. Eventually, the projectile is gonna hit, it's gonna come up. Okay, so now it's decreasing already. Anywhere between t equal to 0.7 and 0.8, the projectile hit maximum height. But it can be the other way too, right? Let's see, it can be, yeah, it can be between 0.6 and 0.7 as well. Anywhere between 0.6 and 0.8 seconds, the projectile hit its maximum height. I presume it's between, yeah, it's going to be between 0.6 and 0.7. It's going to be between 0.6 and 0.7, not 0.7 and 0.8, okay? It's going to be between 0.6 and 0.7. Because, see, this one is higher than this other one here. And the function is symmetric. Now the projectile is decreasing in height. Okay, until it hits the ground. Until it hits the ground. Here you go. 1.2. Okay, now it's already below the ground, right? Minus 0.07. So anytime between 1.3 and 1.4 seconds, the projectile hits the ground. We can do better than that. Let's say, what did I do here? Oh my goodness, I know what I did. Okay. Okay, so we go, let's go. more. Yeah, we can stop here. So it hit the ground between 1.3 and 1.4 seconds. But we can do better than that. Instead of 0.1 seconds, let's do 0.05 seconds to get a finer, right? A higher resolution in our calculations. Here you go. And we're gonna have twice as much data now. So we should stop around here. Let's see. Oh, yeah. Stop here. See, it's already below ground here because of the negative, right? And now that I have the X and Y positions using the parametric equations, we can plot the Y versus X graph to get the motion diagram in the two-dimensional space. That's how it looks like. Okay, that's how it looks like. And because it's 20 degrees, we have to shrink a little bit here in this direction, right? To give the appearance that the angle is 20 degrees. Let's see, more like that. And instead, let's see, yeah, 0 to 5, right? Let me, okay, this distance here is supposed to be equal to, half this distance here is supposed to be from here to here, okay? And I'm going to adjust this guy here, not from -1, but from 0, okay? And that's how the motion diagram of a projectile looks like. Do you see the parabola here, right? 355, I think is a good point. 355 is 1155, right? 1155 is a good point to stop here for the break. And do you have any questions before we go into the break? Two different examples of projectile motion. 11:55 a.m. to 12:10 p.m. And then we're going to move after the break. We're going to cover something else to finish chapter 3, okay? So I see you in 15 minutes. Thank you. Bye-bye. 15 minutes, okay? I'm back here. Okay, so there are many other examples that we can come up with this type of motion, okay, with the projectile motion, okay? One of the things that I didn't do, and I want you to try to do on your own too, okay, is find, for instance, other examples for projectile motion. Find y as a function of x using the equations of motion. Okay, so what you have to do, hint, right? Eliminate t from the equation and obtain from the two equations for x and y, and obtain y as a function of x. That's one possibility. That's one possible example. Okay, another possible example, find the maximum height of the projectile using the equations of motion. the maximum height, I would say, y max, right? As a function of, let's say, initial velocity, theta, initial velocity and theta, right? We need anything else other than that? Yeah, that's all we need. Yeah. Find the maximum height. Okay. Find how long the projectile stays airborne. The projectile stays airborne. Okay. Find the angle of maximum range, right? Using the equations, again, right? Using again the equations, using the other example, projectile motion, okay? Using the equations of motion. One, find y as a function of x. Two, find the maximum height of the projectile reaches, right? Find how long the projectile stays airborne. How long the projectile stays airborne. What else? Find the angle of maximum range. And so on. And so on, right? And so on. Those are all possible problems that you can face in the exam or in the problems that you solve there online. So going back here to we are right here on, okay. So we did projectile motion. And now we're going to do, let's take a look at the right in here. Yeah, projectile motion. We did projectile motion here. Okay. And now, see here, maximum height, right? The range of a kickoff. Range of a kickoff. We just did that. Example 8 in the book. And that's another type of problem too. Okay, range of a projectile when you launch the projectile from initial height. Okay, the equations of motion are similar, but now the initial height is no longer going to be 0, right? It's going to be something else. So what they're going to do now is we're going to do relative velocity. And we'll be able to finish this chapter today. Let's see, 12:16, right? Do we have another half an hour, 35 minutes to do that? Displacement, velocity, and acceleration, we covered that. Equations of kinematics in 2 dimensions, projectile motion. And now let's finish chapter 3, which is relative velocity. And then I will have to update my syllabus, right? So here you go. Yeah, we are going to start laws of motion earlier. Let's put that here. Laws of motion. But we're still behind this lab 1, right? We should put here lab 1. Let's see. Lab 2, we are going to do some other time. Have to adjust here. laws of motion 1. Let's see. That's not lab 3, lab 2. Here is going to be lab 3. Let me erase that. I just so it makes things easier for me. Lab 4, lab 5, lab 6, and laws of motion, lab 1. Let's see here, lab of motion 1, laws of motion 2. I initially scheduled this chapter to go much slower than that, what we're doing, right? And law of motion 3. Maybe you're gonna need, yeah, a little 3 meetings maybe for laws of motion. So, well, maybe 4 meetings. Let's put it this way. Here you go. Monday after law of motion, then you're going to have, oh yeah, we still have to cover uniform circular motion. And then as we move along, I'm going to update this schedule of classes, okay? That's far enough. Save it. Relative velocity. This is a very important concept, by the way. When we cover physics 7, we're going to go back to this concept of relative motion, but through the lenses of Einstein's special relativity. Okay, if you want to understand Einstein's special relativity, which is a very weird theory, you got to understand relative motion. We have to understand this, what we're going to cover right now. Okay, so I want you to have a conceptual idea of relative motion. Okay, in a very good way of having an idea of relative motion, just think about whenever you're driving the freeway, right? The speed that is displayed in your speedometer, is automatically assumed that to be the speed or velocity relative to the freeway, right? The freeway is there at rest. And if your tires has a grip in the freeway, whatever the speedometer shows is exactly the velocity the speed that you have relative to the freeway. Okay, but depending on the referential, you can have different results for the speed of your car, for instance. Okay, this is not necessarily the same speed for different referentials, right? For instance, for instance, suppose you are moving at 60 miles per hour in the freeway, the 405 freeway, moving south at 60 miles per hour in the 405 freeway. Definitely, your speed with your velocity, right? Now, your velocity with respect to the freeway is 60 miles per hour along the south direction. But now I'm going to do that a slightly different problem. However, suppose there is another car next to you, car number 2, okay, that is also moving at 60 miles per hour towards the south direction. Okay, towards the south direction. In this case, car number 2 finds that you are at rest with respect to him, okay? In other words, the velocity of your car relative to car number 2 is 0, because they're moving together with you in the same direction with the same velocity. That's what we call relative velocity. Relative to what, right? Let me give you another example. Now, suppose there is a third car moving north along the 405 freeway at 60 miles per hour. According to the referential of this third car, you would be moving south at 120 miles per hour, right? Is 60 miles in one direction, 60 miles in the other direction. So it is as though as your velocity is the double, it's twice as much, because the velocity of the other car is summing up to the velocity of your car. That's what we call, that's what we, you know, that's the idea of the concept of relative motion. Okay? So we have all sorts of relative motion. We can have velocity of your car with respect to the ground or the freeway. Velocity of your car with respect to the car ahead of you. Velocity of your car with respect to someone else jogging along the freeway. A pedestrian jogging with respect to a pedestrian, right? Jogging along the freeway. You can have velocity with respect to the wind that's blowing outside your car and others. That's what this thing is all about. That's what this concept is all about. And it's very important because you need to know these things. For instance, when you have a ship navigating high seas, for instance, you have to know the relative velocity of your ship with respect to the water currents, for instance. Velocity with respect to the seashore, right? And so on. Okay, and how do you treat that mathematically, right? How do we treat that mathematically? So let's start with one-dimensional example of relative velocity. Here you go, one-dimensional. Two individuals, A and B. A is jogging along the positive direction of the x-axis at the speed of 2 meters per second, and B is walking along the same direction with speed of 1 meter per second. The same direction. What's the velocity of B with respect to A, right? Let's see if I have an illustration here. Okay, right in here. Yeah, I have an illustration here. So what do we do? How do we treat this type of problem, right? So here we have two different joggers. I did an example for cars. Now let's do an example for joggers, right? This is a one-dimensional type of problem. And there is a special notation for that as well. Okay? Individual A, individual B. Here is the referential of the ground. And what you see right in here is the referential of the jogger B. Okay? That's what it is. And this referential is moving with jogger B. With jogger B, no, is the guy that's walking, right? Yeah, the guy that's walking. So at a given instant of time, this guy is here. A little bit later on, he's going to be a little bit more ahead, like that. Can you picture that? Here you go. That's the type of notation that we use for this type of problems, okay? And we use this notation because it is very useful. A little bit later on, the jogger is going to be, let's see, we have oh, wait a minute, I didn't put the jogger moving, right? The jogger must be moving as well. It's not just, and it should be moving further away, twice away, like that. And now I need to stretch my axis. Otherwise, right? A little bit later on. Even further away, here you go. I'm gonna put my X right in here. And this guy is gonna be further down as well, like that. Let's see. First frame of my movie, second frame of my movie, third frame of my movie, right? The distance between A and B keep on increasing because the jogger A is moving faster than the other guy, B. Okay? And let me move it a little bit further away. Yeah. Now it should have something good. Okay? So now what's the velocity of B with respect to A? Okay? What's going to be the velocity of B with respect to A? Because the distance between A and B keep on increasing, according to the referential of A, it is as though as B is moving backwards. Make sense? Okay? Along the negative direction of the axis. Let's see here. A is jogging along the positive direction. Walking along the same direction with the speed of now. What's going to be the speed, the velocity of B with respect to A? Okay, so solution. Because the distance between A and B keeps on increasing as time goes by. As time goes by, comma, and both individuals are moving in the same direction, and B is behind A, okay? Because one, the distance between A and B keeps on increasing as time goes by. Two, both individuals are moving in the same direction. And three, B is behind A, comma, it is as though as B is moving along the negative direction of the x-axis as seen from A, okay? At 1 meter per second. So would be, the notation that we use is like that. The velocity of B with respect to A see that? B with respect to A is going to be minus 1 meter per second. Okay? That's the notation that we usually use. Minus 1, 2. But then this velocity can be written down in a different way as well, okay? Here you go. Velocity of B with respect to the ground. Now the velocity of B with respect to the ground is going to be plus 1 meter per second. Velocity of A with respect to the ground. Velocity of A with respect to the ground is going to be plus 2 meters per second. I want you to get familiar with this notation, okay? This notation is very useful. And then we have another possibility. Instead of velocity of B with respect to A, we can also write that down. Velocity of A with respect to B. In this case, velocity of A with respect to B is going to be plus 1 meter per second. And I'm going to put it right in here, next to the other one. This is no coincidence that one is negative and the other is positive. It's no coincidence that we have BA here as being negative and AB here as being positive. That's how useful this notation is. This notation has some mathematical properties, okay? Okay. G above, big G above denotes the ground. The referential of the ground. Referential of the ground, okay? But this is just a one-dimensional the example of relative motion. Okay, if you want to do a more genetic type of motion that involves the two dimension, things become more complicated, okay? Things become more complicated. And we need a more genetic mathematical model. And the way we do is like that. Here you go. We have here this graph, okay? We represent this axis that you see here, X and Y axis, as being my referential A. And this other axis, X prime and Y prime, as mean by my referential B. Both referentials has an origin. Referential A has an origin O, referential B has an origin O prime. Okay? Here is the vector velocity of the referential B with respect to A. Okay? And there is someone here in this referential observing this other point that's moving with respect to referential A. Okay? Notice that I have vector position of A with respect to B. Vector position of should be B with respect to A. Okay. Yeah, that's right. Vector position of B with respect to A, right? Here's the B referential. Is the vector position that goes from the origin of the referential to the origin of the B referential. Here's the vector position of the point P that everybody's observing. For instance, it can be an airplane, okay, that's flying. And here's the vector position of the point P or the airplane with respect to B. If you look carefully here at this drawing, you're going to notice the following. Let me copy this thing, okay? Take a look. I'm going to copy and paste right here. 10 more minutes to go. Let's see if I can finish that. Notice that this vector that you see right in here that goes from the origin of referential A to the point P is the sum of these other two vectors, okay? Let's write it down. The position of point P with respect to referential A is equal position of referential A with respect to B, this guy right in here, plus position of your airplane, right? Or point P with respect to B. So far, so good, right? But now if you commute those two vectors, you're going to get a very interesting notation that has mathematical properties. Okay, you're going to see. I'm going to commute them. Look what we get. I get point P here on the left, point P here on the right. Right? And then you have referential A here on the right and referential A here on the extreme right. Do you see that? That's the type of mathematical property that I'm referring to. Here you go. Let's take a look at that again. P appears first, P on the left side, P appears first on the right side. A appears last on the left side, A appears last on the right side. And then we have the referential B in between, okay? Notice what a nice mathematical property. Notice the nice mathematical property that this notation has. One, P appears first on the left, and it also appears first on the right. A appears last on the left, and it also appears last on the right. In between, finally, B appears in between P and A on the right. Okay? So it's very easy to memorize just because of this nice mathematical property of this equation that you see here. 4:43, 7 more minutes to go. Okay? So we can extend this notation to velocity vectors as well. We can extend this notation to the velocity as well. Okay? By the same token that we have RPA is equal to whatever you saw there. If you do delta RPA delta T, we are going to have delta RPB delta T, delta RBA delta T, which lends the exactly same notation to the relative velocity. Okay? PP, AA, BB, right? And look what else can we can do. Suppose that I decide to write VP. Suppose that I want to write down here, not VB sub A, not VB, not V sub BA, but V sub AB. Okay? Because I inverted this subscript, we have to add a negative sign here. Okay, because now it's velocity of A relative to B, which is minus the velocity of B relative to A. Okay, I can write that down here. Here you go. Like that. Okay, or, that is a nice mathematical property that this notation hides there. You invert the subscript, you add a negative sign here. Okay. And now we can repeat. Let's see, 5 more minutes to go, right? Let's take advantage of this 5 more minutes. Now we can repeat the problem of the joggers. Not the problem, the example, right? Of the joggers using this important notation. Okay. What we want to do? Find, here you go, the velocity of A with respect to B. Find, let's see, find the velocity of, let me go back here. Here's velocity of B with respect to A, okay? Let's do that. Velocity of B with respect to A using the above notation, okay? And here you go. We use B with respect to A. That's what I want to find out. B with respect to the ground. Oh. Ground with respect to A, right? B here, B here. A here, A last. A last on the left, A last on the right. And in between we have the ground. Velocity of B with respect to the ground is going to be 1 meter per second in the positive x direction. Velocity of the ground with respect to A, the ground seems to be moving away as well, right? Is going to be what? Minus 2 meters per second in the positive x direction. And now we solve this equation and we get exactly what we got before, right? We're going to have, here we go. Take this guy from the parentheses. Minus 1 meter per second. Okay? So next time is 4:49, right? 12:50, 12:49 right now. Next time we're going to do a more complicated problem, not a one-dimensional problem, but a two-dimensional problem, okay? And so I can update my syllabus here. Here you go. We're going to have another meeting on chapter 3. 2, 3, and then we're going to start chapter 4 next time. 2D motion number 3. Let's put it this way. Okay? And it's 12:50 right now. We can stop. And I have a break. I have office hours. If you want to stay around and ask any question, I'll be available. Otherwise, I see you next, the day after tomorrow on Wednesday. Okay? See you
Thank you,
all.
Professor.
Bye-bye.
Thank you, Professor.
Professor.
Yeah. Did you need any help, Isabel? Let me see. Ok. Então. Isso é feito. Soda is mu.
Professor, sorry, did you take roll?
No, I didn't. I didn't. I take roll only the first 2 weeks.
Oh, okay. Sorry. I went out to the restroom.
Okay.
Is class over?
Yeah, it's
Okay.
12:55. Yeah. Uh-huh.
Okay, thank you, Professor. Have a good rest of your day.
You too. Bye bye.